Good morning, everyone. Okay, so we're going to start with 6.3, talking about the absolute value graph. So what I want everyone to do right now is to get their calculator out. We're going to use it for a little bit. You know that doesn't always last long in this class. But go ahead and get that out. And I want everyone to graph the equation 2x minus 4 in their calculator. So I want you to see the calculator. I want you to look at it. I'm going to go ahead and pull it up on Doceri for you, just to show you what that looks like. So here is the graph, y equals 2x minus 4, just a line. Now the second part, so number 2, it says leave the original line and graph y equals the absolute value of 2x minus 4, and then look at the differences between the two. So I'm going to add that. Take it away. And I want to write a few things that you notice about the two graphs. So the difference between the line and the absolute value. I'm going to go ahead and draw that for you. So the purple is just the line, and then the green would be the absolute value. And so if I were to look at the difference between the two, the absolute value is always above the x-axis. So absolute value equation is above the x-axis, meaning it never touches below. And it also, if you can kind of imagine, it takes this negative part of the line and it flips it up. So below is flipped up. So essentially the absolute value is just like the line, but everything that is below the x-axis, which this is my x-axis right here, every part of that equation that goes below is now, imagine it reflected above. So this part below the x-axis is a mirror image now flipped up above the x-axis. And it also connects with our concept of the absolute value, because if you think about it, everything that is inside, any negative that is inside an absolute value now becomes positive. So the negative part of the graph becomes positive. And that is just like these two lines, so the absolute value lines, make everything positive. So you knew we were going to do it, but it says put your calculator away. So I want you to put it up and graph the line y equals negative 3x minus 1. So when you see an equation that's in standard form or slope-intercept form, I'm going to start with the y-intercept, which would be negative 1. Put a point there. And my slope is negative 3. So that means I'm going to go down 3, right 1. Go in the opposite direction. Connect the dots. I know sometimes we are still struggling with how do I know to go down or to go up. And so a negative slope, it's like reading a book. If you're reading a book from left to right, so if I'm reading this book from left to right on the graph, it is pointing downwards. That means it's a negative slope. So remember that. I'm going to go down 3, right 1. Down 3, right 1. And then to draw it to the left, the opposite direction. Now if I were to graph the absolute value of negative 3x minus 1, everything that is negative, so all this part right here that is below the 0 or below the x-axis, is going to be flipped upward. Okay, so I'm going to use a different color. I'm going to take this part and flip it up. So the absolute value is just everything above the x-axis. All of the negative part is now flipped up. It's like a mirror image. So this just got flipped to be above the x-axis. So the basic absolute value equation, just very basic, is y equals absolute value of x. And we call that a parent function. We've actually learned several parent functions so far this year. You may not have even noticed, but like the parent function of a line is y equals x. And the parent function of a parabola is y equals x squared. So when I reference a parent function, all I'm saying is the most basic form, like without any transformations added to it. So no shifting left or right, up or down, no stretching, condensing, none of that. It's just the most basic absolute value equation. And then we'll add transformations to that later. So characteristics of the graph, I'm actually going to draw it for you first. It has a point at 0, 0 and a slope of 1 on each side, so it looks like a V. You might have seen these equations before. I think you might have graphed them. But the graph looks like a V with a slope of 1. If I were to read the domain is going to be all real numbers, so negative infinity to positive infinity. And we always attach parentheses to infinities because it never actually touches it. You could also write all real numbers. In the range, I'm reading from bottom to top. So the lowest point that this graph will ever touch in the parent function form is going to be at 0. And that does have a bracket attached to it all the way to positive infinity. Goes on forever. Or you could say y is greater than or equal to 0 if you're doing interval inequality notation. So in the last unit, when we talked about vertex form of a parabola, so kind of think back. That's why it has the word throwback in there. Think back to what did each number do to the graph when you were graphing it? So if I were to graph this equation, I've got this 4, this plus 2, and this plus 3. So the 2 on the inside of the graph, that shifted it 2 units to the left. So remember, if it's plus 2, you're going to do the opposite sign. Opposite sign. So it goes left 2. The 3 on the outside moves it up and down. You keep the sign on the outside. So that means that it goes up 3 units. And the 4 on the outside was essentially what we called the beginning slope. So whenever you went left 2, up 3, you would put your vertex or your point there, and then from there you would go up 4 over 1, up 4 over 1 on each side. So it was the beginning slope is 4. And I put slope in quotation marks just because, you know, the only true slope is for a line, but we use the term loosely as slope because we're still going up 4 over 1. Well, these transformations are actually true, or they stay the same, for absolute value graphs as well. So we're not having to learn anything new. I'm going to put an exclamation point there because I'm so dang excited about it. Absolute value graphs have the same transformations. So thinking back, that's why I'm just trying to show you that everything in this class connects with each other. So the vertex form for a parabola is very similar to the vertex form of an absolute value. Here we have parentheses with a squared on the outside, so parentheses in the squared. If I were to take that away and just put absolute value signs there, it would still do the same thing. It would just look like a V instead of a U. So kind of cool. So we're going to look at some of these graphs. I encourage you to maybe pause the video and try these on your own and then just check them at the very end. But I'm going to go through and explain each one just in case maybe you got one wrong. Then you can maybe hear my explanation for this. So all of these vertexes, is that the plural form? All of these vertexes are going to start at 0, 0. They're going to look like the parent function, and then they're going to shift left, right, up or down, and then we're going to look at the slope on the outside to determine where to go from there. Also, remember, we didn't talk about this in the last example, but if you have a negative sign in front, that does flip, so where the V now looks upside down, or it's flipping downward. Okay, so we're going to go through all of these. Do not use your calculator on these. I want you to try them on your own. So if we're talking through this, we have y equals the absolute value of x minus 2. So that minus 2 means that it goes down 2 units. Slope is still the same. It's still pointing upward. So I'm just going to put little dots going up 1 over 1. And that way that I can kind of connect the dots. And you only have to really go out 1 on each side, but you can still keep going if you want, just to make it more accurate. It is going to follow the same slope continually, unlike the parabola where you only went up and over 1 time. You can keep going up and over forever on these. Number 2, x minus 2. Now the 2 is in parentheses, so that means that it's going to be shifting right 2. Still pointing up. Number 3, going left 3, down 1. So left 1, 2, 3, down 1. I'm still pointing up with a slope of 1. Number 4, I've got this negative. That just means that it flips over the x-axis. So now it's going to be, I'm keeping my vertex at 0, 0, but it's now flipping down. Number 5, I've got this negative, so it flips. From there, it's going to go left 1, up 3. So flip the x-axis first, goes left 1, up 1, 2, 3. Still has a slope of 1, but now points downward. Number 6, flips the x-axis, right 3, down 2. So flip, right 3, down 2. It's going to be pointing downward. Whoops. Okay, last 3, I now have a number in front. That means that my slope equals 2. It doesn't go left, right, up, or down any. So I'm going to stay at 0, 0. I'm going to go up 2 over 1. Stays consistent with that slope forever. And the reason being that it doesn't do that in a parabola, but it does in absolute value, because my degree is still 1. With a parabola, my degree is squared, so it's exponentially getting steeper. Number 8, it now flips. I have a slope of 3, and it goes right 2. So I'm going to flip it first. I'm going to go right 2. Got my vertex at 2, 0. Now my slope is 3, so that means I'm going to go down 3 over 1, down 3 over 1 on each side. You could also think about like putting this together. The slope is -3, so that means I'm going to be going down 3 over 1. And then last one, I have 1/2 in front. It's going to go left 1, down 3. Left 1, down 3. It doesn't flip or anything, but the slope is now 1/2. So I'm going to go, if you remember this, I'm going to go up 1/2 over 1. You remember that? Up 1/2 over 1. Up 1/2 over 1. So you go up or down, whatever the slope is, over 1.